Hello everyone, the subject is EC3501 Wireless Communication. Third unit is Modulation Techniques, Equalization and Diversity. Today we are going to see about the spread spectrum modulation techniques. These are the topics in third unit. So let's see the spread spectrum modulation techniques. All modulation and demodulation techniques achieve greater bandwidth and bandwidth efficiency. Since bandwidth is limited resource, the primary design objective of all modulation scheme is to minimize the required transmission bandwidth. So we are using spread spectrum technique. It employs a transmission bandwidth greater than minimum required bandwidth. The system is bandwidth inefficient for single user, but the advantage of spread spectrum is that many users can simultaneously use the same bandwidth without interfering with one another. So these are the characteristics of spread spectrum signal. They occupy very large bandwidth and it is pseudo-random in nature. They have noiseless properties. Spreading waveform is controlled by a pseudo-noise sequence or pseudo-noise code. Spread spectrum signals are demodulated at receiver through cross-correlation with locally generated version of pseudo-random carrier signal. Let's see about the cross-correlation. Cross-correlation with correct pseudo-noise sequence despreads the spread spectrum signal and restore the modulated message. But cross-correlation of the signal from an undeserved user results in a very small amount of wideband noise at receiver output. Let's see about the PN sequence, that is pseudo-noise sequence. It is the binary sequence with an autocorrelation that resembles over a period the autocorrelation of a random binary sequence. It has many characteristics similar to random binary sequence. The characteristics are they have equal number of zeros and ones and very low correlation between the shifted versions of the sequence and very low cross correlation between any two sequences. This PN sequence can be generated using sequential logic circuits. This is a block diagram of a generalized feedback shift register with M stages. This circuit will generate the PN sequence, that is pseudo-noise sequence. There are several stages. Clock pulse is also applied. There is a feedback logic. The output is PM sequence output. So here we have the feedback shift register. It has consecutive stages of two memory devices and feedback logic. Binary sequences are shifted through shift register in response to clock pulse. The output of various stages are logically combined and fed back as input to the first stage. When feedback logic has exclusive OR gates, then the shift register is called linear PN sequence generator. So the first type is direct sequence spread spectrum. The direct sequence spread spectrum spreads the baseband data by directly multiplying the baseband data pulses with PN sequence. There is a single pulse or symbol of PN waveform is called chip. So this is a transmitter used for direct sequence spread spectrum. Here the message is the input and output is the signal that is to be transmitted. Here we have the PN code generator, then we have the band pass filter, and then there is an oscillator that generates the carrier frequency. So the received spread spectrum signal for a single user is denoted by capital S. It is equal to root of 2 ES by TS, M of t, P of t, cos 2 pi FCT plus theta. Here we have M of t, it is data sequence, P of t is the PN spreading sequence, FC is carrier frequency, theta is the carrier phase angle. So M of t we know it is data or message. It is a time sequence of non-overlapping rectangular pulses, each of which has the amplitude equal to plus or minus 1. Each symbol in M of t is data symbol and it has duration Ts. And PN spreading sequence is denoted by P of t. Each pulse in P of t is called as chip. It is the rectangular pulse, each of which has the amplitude equal to plus or minus 1. The duration of this is TC, denoted by TC. So this is the pseudo direct sequence spread spectrum receiver. Here we have the wideband filter, then we have the coherent phase shift keying demodulator, and then we have the synchronization system PN code generator. So let's see about the receiver. The received signal is passed through wideband filter and is multiplied by the local replica of PN sequence P of t. If P of t is plus or minus 1, then P square of t is equal to 1. This multiplication yields the D-spread signal S of t, and it is denoted and it is given by the expression given below. Since S1 of t has the form of BPSK signal, the corresponding demodulation extracts the message signal, that is M of t. So this is the spectrum of desired received signal with interference. So the first one, it indicates the wideband filter output, and the second diagram, it indicates the correlator output after despreading. And for spread spectrum technique, we have an important parameter that is called as processing gain. It is denoted by Pg. It is nothing but Ts divided by Tc. Ts is simple duration and Tc is chip duration, or it is denoted in terms of rate, that is Rc by Rs. Greater this processing gain, greater will be its ability to suppress the in-band interference. And the second type is called as frequency hopping spread spectrum. It involves a periodic change of transmission frequency. This can be regarded as a sequence of modulated data bursts with varying random carrier frequencies. Here we have some important terms. First one is hop set. It is a set of possible carrier frequencies. Hopping occurs over a frequency band that includes a number of channels. And the second parameter is instantaneous bandwidth. It is nothing but the bandwidth of the channel used in the hop set. And the third parameter is total hopping bandwidth. It is bandwidth of spectrum over which the hopping occurs. So this is the block diagram of frequency hopping spread spectrum transmitter. Here the input is the data or the message, and the output is the frequency hopping signal. Here we have the modulator circuit, oscillator circuit, and PN code generator and frequency synthesizer. This is the transmitter block diagram. So first, let's see the operation of the transmitter. Data is sent by hopping the transmitter carrier to random channels which are known to the desired receiver. On each channel, small bursts of data are sent using conventional narrowband modulation before the transmitter hops again. If single carrier frequency is used on each hop, digital data modulation is called as single channel modulation. So here we have the hop duration or hopping period parameter. It indicates the time duration between hops. It is denoted by Th. So the processing gain in the case of spread spectrum, that is frequency hopping spread spectrum, is calculated by using the formula WSS divided by B. Here WSS is nothing but total hopping bandwidth and B is the instantaneous bandwidth. Then let's see about the receiver. Frequency hopping spread spectrum receiver. Here the input is the frequency hopping signal and output is the actual message data that is transmitted. So here we have several blocks. They are wideband filter, bandpass filter, demodulator. Then we have the PN code generator, frequency synthesizer and synchronization system. So in frequency hopping spread spectrum, we have two types of frequency hopping. One is fast frequency hopping and another one is slow frequency hopping. So fast frequency hopping occurs if there is more than one frequency hop during each transmitted symbol. So hopping rate equals or exceeds the information symbol rate. Let's see the second one, slow frequency hopping. It occurs if one or more symbols are transmitted in the time interval between frequency hops. So now let's see the modulation performance in fading and multi-path channels. Here we have to see some three topics. One is performance of digital modulation in slow flat fading channel. Second one is performance of digital modulation in frequency selective mobile channels. And last one is the performance of pi by 4 DQPSK in fading and interference. Here we have let's see the probability of error. In the case of slow and flat fading channel, the first one indicates the probability of error, and for railing fading channel, the second expression is the probability of error. And for large values of EB by N0, that is energy per bit by noise ratio, here the probability of error is simplified as follows. For PSK, the probability of error is 1 by 4 gamma, and for FSK it is 1 by 2 gamma, and for DPSK it is 1 by 2 gamma, and for non-coherent orthogonal BFSK it is 1 by gamma. So the probability of error in slow and flat fading channels are evaluated and the expressions are given below. This is the waveform that indicates the performance of digital modulation in slow flat fading channels. Here the performance of FSK coherent detection, FSK non-coherent detection, DPSK and PSK are shown in the diagram. And this indicates the performance of digital modulation in frequency selective mobile channels. The bit error rate performance of different modulations with coherent detection for a channel with Gaussian shaped power delay profile is represented here. The parameter D is the RMS delay spread. It is normalized by the simple period. So here also the comparison of coherent detection is given here for the modulations BPSK, QPSK, OQPSK and MSK techniques. And next the performance, the same set of curves are plotted as a function of RMS delay spread normalized by bit period. So here also the coherent detection for the following modulation methods are used. One is BPSK, second one is QPSK, then you have OQPSK and last one is MSK. The different performance curves are plotted and it is shown here. And this block diagram, it indicates the actual digital modulation system. The first one is the actual digital modulation system and the second one is the digital modulation system based on baseband digital hardware simulator with software simulation as a driver for real-time bit error rate control. So in the normal actual digital modulation system, we have the data source. Data source may be TV camera, optical scanner and computer terminal. Then we have the modem. Modem is nothing but modulator come demodulator. In the transmitter section, we are using that as modulator, and at the receiving section, we are using that as demodulator. In between that, we will be having the channel. Here we are having the fading channel, and at the end, the last block is data sink or data destination. It may be the TV screen, fax machine or computer terminal. So this figure shows the bit rate performance of pi by 4 DQPSK modulation technique in slow flat fading channel corrupted by interference. This is the bit error rate performance versus EB by N0 for the same pi by 4 DQPSK modulation technique in railing flat fading channel. And this is drawn by varying the mobile speed. At frequencies FC it is equal to 850 MHz and FS it is equal to 24 kilobits per second. This indicates the bit error rate performance of pi by 4 DQPSK in a two-ray railing fading channel where the time delay rho and the power ratio C by D between the first and the second ray are varied. So this is taken from the textbook Wireless Communication by Rappaport. Thank you.